where we arrived yesterday. So yesterday we saw the Kelvin waves and Poincaré waves. Okay, can you remember what is the thing that they have in common? You remember what we said about the frequency? You remember? You don't remember? You should remember. So, sorry? No, please go.
No.
You wanted to be sacrificing. Okay, so we said that for Poincaré and Kelvin, mostly we have that omega is much larger than F. Okay, so Poincaré and Kelvin waves are super inertial waves. Okay, so the frequency is much larger than F. Then we said, okay, is there any wave phenomena which is slower, possibly associated with the evolution of disturbances in the geostrophic flow? So at the end, what we obtained is that the planetary and the topographic wave that we see today are characterized by the fact that omega is much smaller than F or order than F, while Kelvin and Poincaré have omega larger, at least from F to larger values of F, so higher frequency. So these are called super inertial, while the other one are sub inertial. Why sub inertial? Because we are looking for something that gives a perturbation to the geostrophic flow. Okay, so we have our geostrophic flow, and as we said that we saw yesterday, we want to put some perturbation. So the first perturbation that we said is, okay, I represent my Coriolis parameter as the sum of the mean Coriolis parameter when I am on a central latitude, phi 0, and then I relax the F-plane approximation in order to consider a larger area, okay? So a larger distance, meridional distance, so Ly specifically, with respect to what I consider when I work with the F-plane. So this is the beta plane approximation. So when I have the beta plane approximation, I can represent F, you remember, as the Taylor expansion. So beta 0 is 2 omega, the radius of the Earth, cosine of phi 0. Okay? While this is the usual 2 omega sine phi 0. So yesterday we used A, no? Here. Okay. So this is much. So when we have the scaling of this, we will have that beta 0 L over F0 is much smaller than 1. Okay, so this is actually a perturbation, this term is actually a perturbation of the Coriolis parameter. So with this perturbation, and we call this number here as planetary or beta parameter number, while beta 0 is the beta parameter or the planetary parameter. So if we substitute this expression here in our momentum equation, so we will have not just F, but F0 plus beta 0 y v, which is equal to minus g dx eta, then ETV plus F0 plus 0y u.
Is that any one or revision?
Sorry?
Is that a revision?
Is that, yeah, we were starting from yesterday. You need a coffee more, huh?
What's the difference between the F-plane and the beta plane?
So, what's happening in the F-plane? You remember, when you did F-plane, we said that df over dy is equal to 0. So if df is equal over dy is equal to 0, it means that this term does not exist. And with this, we can restrict over a very short distance. So L, the zonal distance is much smaller. And what we obtain is that the horizontal divergence is equal to 0, okay? Which was one of the characteristics of the geostrophic flow, right? What we obtain in the beta plane is this one. So in the beta plane, we no longer consider, of course, the F plane, and we give the opportunity to F to be a function of Y through the beta parameter, okay? And beta 0 has a very, very small value. So it's 10 to the minus 11 meter minus 1, second minus 1. So actually, this is exactly, has the same idea of the Bus-Inex approximation. Okay? So this term here is always much smaller than this one. Like rho prime was smaller than rho 0. Okay? So the idea is always this one. So what is, so we have like sort of steady flow, steady situation. We are inserting in this steady situation some trigger, some perturbation. This is the perturbation that we are inserting within the geostrophic flow. So if you look here, let me just conclude this. So if you look here, you can recognize that we have F0 V equal to minus G dx eta, F0 U equal to this, and this. So these three terms here, I mean, these three equations, this equal to this equal to this, and this equal to 0, gives us the geostrophic flow in F-plane, okay? So if we add the time derivative, what is the meaning of the time derivative? Because we need to have something like, you see yesterday, like kx minus omega t. So we are interested to this omega, okay? If we have dt equal to 0, we don't have any kind of evolution of wave, so we don't have a wavy phenomenon. So that's why we retain this, allowing Rossby temporal number to be ordered than 1, and neglected the non-linear terms. Okay, so we can try to solve this. We know that from the geostrophic flow, we have that V is equal to G F0 dx eta, and U is equal to minus G F0 dy eta. So these are the solution, let's say, Cushman calls large-scale terms and small scale terms. So large-scale terms are this and this. The small term are this and this. As we said before, so when we have large-scale terms, it means that we are we are satisfying the geostrophic approximation, right? When we add the small term, we are giving the perturbation. With the perturbation, we create and we trigger the wave. So if we solve this for the large term, and then we put this solution here within the small term, what we will obtain will be, so this will become, so we have a variation of time, so we have G F0 dx t eta minus F0V minus beta 0 y multiplied by V, so it's G, sorry, this is minus, so this is U, minus, okay, G F0 dx eta equal to minus G dx eta. The second is the TV, so V is this one, so is G F0 dxt eta. Then I have the Coriolis term, and then I have plus beta 0 y, and then I have u, which is this one. Okay? So what I did was to simply substitute the solution of the large term within the equations, the partial differential equation, and what we obtain, so I can do the contrary. And from here I can solve from u and v. So from u I will have minus g f0 dy eta, this and this, and then all the other terms, minus g f0 dxt eta divided by f0, then this minus beta 0 y f0 with a plus because it's on the other side. This g square dy eta. And the same here, v, which is g f0 dx eta, and then all the other terms. So this is v, so it's minus, so it's plus, this is minus. And this. So the solutions of u and v for this case has still a part which is geostrophic and another part which we call ageostrophic. So this part here actually so this part here depends on the second derivative of eta, on the first well, on the spatial and temporal derivative of eta, so it's a second order terms, and here depends on beta 0 and y. So if we take this one and we put in this in the third equation, so in the continuity equation, because now we have everything as function of eta, okay? So u and v are functions of eta. All the other terms are parameter, g, f0, beta 0, and then we have y here. So we can put everything together. The two terms goes inside, and what we obtain is a single equation for eta. So we have the first term, the local derivative, minus r square, the t, horizontal gradient Laplacian of eta, minus beta 0 r square dx eta equal to 0. So of course, this expression is quite difficult to solve, but we can still remind that we know that our solution will be like this one, like they will have Fourier-like expression. So if we put this within this expression, of course the expression will be quite simplified. And what we obtain is again an expression for omega. So it is an expression omega which depends on the wave number. So it's again the dispersion relationship. So this actually is the most important thing. You can like remember, I mean, how we arrived to this expression, but this is the most important thing that we have to remember about the Rossby waves. So Rossby waves have an expression of the frequency which, which depends on beta 0, r. R is the Rossby deformation, radius of deformation. Then we have kx, the zonal wave number, and then we have a denominator which is 1 plus square of Rossby radius, and then the square of the wave number, of the horizontal wave number. So if we have, analyze this function, so how omega change with respect to kx. So we fix ky, okay? So we fix the meridional zone wave number, and we let omega to vary with the kx. So it's something like this, okay? So this is omega order kx. So if I calculate Cx. So Cx is the phase velocity along the x direction, okay? So along the zonal direction. So Cx is equal to minus beta 0 r squared over 1 plus, let me write, k squared r squared. So all these terms here are positive, right? Sorry?
So finally the phase velocity is negative.
Exactly. So phase velocity in x is negative, so it means that Rossby waves only propagate their phase westward, right? So this is the most important, one of the most important thing of the Rossby waves. So they propagate westward. When we calculate the group velocity, so this is Gx, the G. So to calculate the derivative of the frequency with respect to the wave number over x, which is this one, you know that we have one part, so the derivative of this is the sine of the derivative of this function, okay? So here we are having the function which is increasing. So here we have the kx omega positive, like here.
So the equation,
This one,
yes, you got it from,
this is omega,
yes, that is when it is on the horizontal. We are looking at the horizontal.
only on the x,
So
yes.
the vertical is 0, the ky is 0, it goes to
Ky, you can fix ky. I mean, there is no problem about that. You can fix it and keep it constant, for example, and see what happens, because Cx is omega over kx, right? You remember? So we just have to remove this. And we can fix ky. It's not a problem, it's a parameter. We are most interested on kx. So you can keep the length, the wave number over the y direction, because at the end what you have is things like this moving, right? So this is k, and this is kx and ky. So if you like, you can just change the frame of reference. So it's important to have just one.
In that, can you please explain to me how you get the next equation?
This one?
Yes.
Because Cx, so the phase velocity in the horizontal direction, is equal to omega divided by kx. This is the definition, appendix B of Bushman. Huh? So if I do omega divided by kx, I obtain min minus beta 0 r squared divided by 1 plus r squared, and this sum is k squared.
Okay, thank you.
So what it means here, so we are having that this,
Both of them are 0.
sorry,
The k omega is greater than 0, greater than 0.
is greater than 0. Yes, I was just saying. So if y is, you were saying why they are positive? Are you sure of this question? So how is the function omega kx here and here?
Okay.
Is
Increasing.
so when a function is increasing, the first derivative is
Positive.
positive.
So positive.
Okay? You need one more coffee. Okay. These things are absolutely available here, not during the exam. Okay? So here we can you can say the worst thing that you can, and because I know that something you can like, because this is quite basic. So we are saying, topographic waves, something very well, but this is basic. This is mathematic analysis 1. Okay, so increasing, derivative is positive, derivative is positive. So if derivative is positive, it means that the group velocity is positive, so is eastward. In this section here, we have that the derivative is negative. Okay? So in this part here, the group velocity is eastward. In this section here, where the derivative is negative, because the function is decreasing, we have that the group velocity is negative, so it's westward. So this part here can be relying on small wave number. So when there is small wave number, I can say that I have large wavelength. On the opposite, high here is short wavelength.
Sorry, that's part again.
So kx is the wave number. So kx is 2 pi over omega x. So which is the,
Okay.
okay? So if it is small, means large.
Yes.
And so this was the idea of Rossby. Rossby said, okay, wow, so I have a model which tells me that my wave, because I am Rossby, so I call wave like with my name. So if I am in the northern hemisphere, and if I have, because of the planetary effect, so I have that large waves are going westward, and the shorter waves are going eastward. So this is nothing more than the subtropical jet, and this is the polar jet. Okay? So very easily explained. Very easily explained. Of course, this is just, if you are on Jupiter, that is quite easy. On our Earth we have topography, we have mountains, but basically, this is the idea. So energy is going in this direction, close to the equator, and is going in the other direction, close to the pole. Okay? So,
Sir, could you please explain again about this, that soft tropical jets?
so this is the large scale, and this is the large wavelength, and this is the short length wave. So the idea is that my observation, if I observe, I can see that if you look at the general circulation, you see that you have waves going in this direction, which are larger. I mean, the length is much larger. So this is exactly what you can see from the satellite. And here you have other things. I mean, the mid-latitude typical weather phenomena, which goes eastward. Okay? So with this model, I can explain this. So the Rossby waves are actually this subinertial wave phenomena, which explains you the way the atmosphere is moving over the Earth. Similar also in the ocean. The ocean is a little bit difficult, but because you have the continents. But on the Pacific, you can do it. So if you go the idea of the Rossby waves apply to the ocean, especially in the Pacific, you can have the same. Okay, so this expression, so the dispersion relationship, can be also represented in this way. So in this way, we are having two axes, which are kxr and kyr. Why? So if we rewrite the dispersion relationship by taking, so explaining everything in the plane kx, ky, or kxr, kyr. So this is dimensionally is meters to the -1, right? This dimensionally is 0 or 1, because it's one inverse to the other. So what we can find is this expression here. So it's kx plus beta 0 to omega square plus ky square equal to beta 0 square for omega square minus 1 over r square. So what I'm trying to say is, if I fix omega, so I can take different values of omega, like I have a spectrum of frequency, I take one single value, and I rewrite everything by letting vary kx and ky. So I can find from this formula here. Do you recognize which kind of formula is?
Equation of circle.
Of?
Circle.
Of a circle. So in the kx, ky plane, or kxr, kyr, whatever you like, we can say that the center of each circle with omega constant is when, so the center will be in minus beta 0 to omega 0. And since this is the radius of the circle, of course this must be positive. It's a radius. So from this we can find a value if you work a little bit of this, because it means so beta 0 squared for omega squared minus 1 squared. So we have this, so we have that omega square smaller than so omega the maximum values or maximum value of omega is beta 0 r divided by 2. So the maximum frequency for Rossby waves is based on the beta parameter and the Rossby radius. So that's very important because the Rossby radius depends on f and on g and on h. So according to how this expression here, where we are, if we are in the, let's say, higher latitude or lower latitude, if we have how much, well, also this depends on the latitude. So, but in any case, we have a maximum value, and when we have this value for omega, we will have that this term will be equal to 1, right? Because if we put there is one here. No. Yes. So if we rewrite this in function of kr, we will have this here 1, which is the maximum, correspond to the maximum value of omega. So when we move far from the center, we will have omega 3, omega 2, omega 1. And so you may imagine this circle to become larger and larger, but never going on this direction because the center must be always on the negative side. And when we reach the maximum, when we reach omega equal to 0, so when omega is equal to 0, we have that the circle is so big to be parallel to ky. And when omega is equal to 0, what we have? What do we? Then? When omega is equal to 0, omega is equal to 0.
No oxidation.
We saw it also for the Poincaré waves. Omega equal to 0 means that you lose the dependency on time. And what you have, if you lose the dependency on time, you don't have any more perturbation. So you come back to geostrophy. Okay? So this is the limit of the geostrophy. And from here you can also play with a little bit with this diagram, which is quite nice. And you can see that the group velocity, which is always, so Cg is perpendicular to the gradient Cg is equal to the gradient of the frequency. So it means that it will be perpendicular to the line of equal frequency, the isofrequency lines. Okay? So it means that if it is perpendicular, of course, it will go always in this direction. And it will be always like this because the group velocity can have, will point always toward the center, while the direction of propagation, which is simply related to the phase velocity, will be always in this direction, always with kx, with the cx negative. Okay? Good. So this was the first example for subinertial wave, subinertial paratropic wave, which was very helpful to explain us a very important phenomena, which is characterizing the GFD phenomena. Here it's real GFD, okay? So because we have slow and large flow, okay? So Rossby waves is one of the most important things that you have to work with, to know very well. This is just a very easy introduction. But there is a lot of work who has been made. Riccardo Farnetti is a very big expert of Rossby waves. Okay, so
Sir, how can we differentiate the phase velocity and group velocity in the context of direction of propagation of wave? Because if phase velocity is negative, so the wave is propagating in the westward direction.
the phase.
Yeah.
But the group velocity is the envelope of all the phases. So you can have packet of this, and the envelope looks like a fish. So this phase can go in this direction, but the energy can go in the other direction. So this is really the basic of wave dynamics. You can have, you can really consider, say, well, Cx is simply the ratio between the frequency and the wave number. Okay, so it's the velocity of one single phase having k and omega as wave number and frequency. When I do the variation of frequency among the whole spectrum, and I see how it behaves, let's say, as a whole, that's why I have the group velocity. So the group velocity is related to the whole behavior of the waves. If I wouldn't have dispersion, like for the Kelvin waves, Kelvin waves do not disperse. Rossby waves, Poincare waves, and we will see also the next one, the topographic waves, all of them have a dispersion relationship. So you will always have a function of k, with omega as a function of k, so you will always have a group velocity. So, and you can have things like this. Otherwise, you will have only simple phase traveling without any kind of dispersion. Okay?
Without energy propagation.
Without, exactly. Because dispersions means energy dissipation or not. Okay? That's why, sorry, the surface gravity waves, which are simply this one. And this is actually the phase velocity. So it's constant. It's positive. So you don't have any kind of dispersion. And there is no, there is no group velocity because omega is constant. This is zero because you don't have any dependent. So that's why tsunamis, which travels yeah, like gods, no? Which travel as surface gravity waves, they do not disperse the energy, and this is why they are so dense. Tell me.
No, I think
Okay.
it was something you said. So
Okay, good. Okay. So it's important that you review the wave dynamics because it's at the basis, and you will always have some relation with waves. Also, if you will work in oceanography, I don't know how many of you are mostly the one who are working with the solid earth. Of course, they will have to work with waves, even if they are different waves. But the other one, maybe you will be mostly or all on the atmospheric side. No, I think. No one interested in oceanography? You? Okay. But this is Riccardo is very good in that. So his works in GFD in the Atlantic are very, very interesting. Okay, so we analyzed one kind of perturbation. Now we can analyze a second kind of perturbation. So I already mentioned it as topographic. So we say that if we consider again the usual layout of our system. So let me put Y here, Z. This was eta, and this was H. So you remember that at the beginning we called this H.
Yes.
Then we said that H is equal to H, capital H plus eta. Then we found all the expression in the equations for eta. Now we want to say something more. So let's consider the fact that we have an H0, so a mean or average height, and then we have the topography, which again, this can be atmosphere or can be ocean. No way, Justin. Don't forget to change the density value. So this section here, which here is 0, for example, and here increase going along y, we will call it alpha 0 y. So from this perturbation that we had at the beginning, that we consider for the Rossby wave, we will have something similar, which is h equal to h0 plus alpha 0, I think, y. And then you will see why we are using y. So again, this is a perturbation, because I want that alpha 0 L over h0 is much smaller than 1. And I will call this alpha 0 L h0 as the topographic number. Well, very, not so much fantasy. So, perturbing effect is small and associated with weak bottom irregularity, which are not uncommon in the GFD phenomena. So you can have mountains, you can have hills, you can have mountain ridge, you can have mountain ridge in the ocean, and so on. So the bottom is inclined. We have H as the beginning, which was equal to eta plus H0 plus alpha 0y. So what happens to our equation? So we have H that insists only in the third equation, which was the eta plus capital H, the xu plus dyv equal to 0. So now we have to change this and to substitute with the h0 plus 0y, the xu plus the y. Okay, so no, let me check. So we have to make one step behind, because otherwise we lost something. So this was, yes, because the form that I wrote before was already approximated when we considered the first approximation. I mean, the approximation that we when we worked was on eta plus capital H. Okay, so we have to restart from the first expression. So we will have eta plus h0 plus alpha 0 y u plus dy eta plus h0 plus alpha 0 y equal to 0.
Which expression is this?
So this is the continuity equation, where we have considered one step before the one that we considered, the one that we analyzed 2 days ago. So is the one that works for all the cases except the topographic waves. Because if we consider this and we have the topographic wave, we cannot consider fully, because H here is not just simple to substitute H0 plus alpha 0 y. Okay? So we have to consider the real one, the one which comes from the shallow water model, and to start from this, which is the x, h, this was h, and this was h. Okay? So this is the equation that we had from the shallow water model. Then we arrive to this one by making some approximation, which in this case are not useful. So we have to be a little bit careful. It's like to take to neglect the buoyancy effect. So it's not if you want to see the effect of this perturbation, you have to work a little bit more on this one. So that's why we have to come back and to start from this one. So if we express each single term,
So,
First eta. E was the first.
eta is function of t, yeah?
yes,
And what is eta dependent on x and what?
yes. In the most general case, eta is function of x, y, and t, and h0 is constant, and alpha 0 is a constant, but it must be multiplied by y. Okay? So alpha 0 is a number, because this is of course, is a depth. So this is only a parameter. It's just the tangent of the bottom topography.
So S naught plus alpha y could be taken out from the dx expression, yeah? Because
Of course, sure. But not here.
okay. Yeah.
That's why if we work on the simplified continuity equation, we will lose this term here. Because working a little bit on this, so what we obtain is dt eta plus h0 dx0 plus dyv plus alpha 0v equal to 0. So, would you like I do all the passage?
Yes.
How many for yes, how many for no? Because they are, on the Cushman they are, it's always the same case to taking delta H over blah, blah, blah. So if you do, I think, okay, so it's quite easy. The most important thing is that exactly as Prakash said, the key point is this one. Because from this part, it's exactly the same. From this part, is exactly the same. So the real thing that changed is this one. Okay? Because this is exactly like H we had before. And these are constant. Okay? So this is exactly the same. So what we obtain is this new term. So again, if we put together with the momentum equation, we can recognize again large term which give us the geostrophic approximation, and small term here and here. So for the Rossby waves, it's very nice to have this. There is not the same analogy between Kelvin and Poincaré. Okay, so Kelvin is one specific case of Poincaré, or Poincaré is one most correctly. Poincaré is one specific case of Kelvin. But here, between the Rossby or planetary waves and topographic waves, there are so many analogies. We will see now in the dispersion relationship. So again, if we calculate the the two solution for the geostrophic flow. So it's minus G over F0 dy eta, G over F0 dx eta. Then we put inside, we make all the calculation, and what we obtain is again that U and V are again dominant term, which is the geostrophy, plus a term which is GF squared minus second derivative xt eta and G f squared second derivative yt eta. So again, as in the Rossby, we have that solution is the dominant geostrophic flow plus a perturbation of a order, of a lower order. Okay? So this is actually what you have because of the perturbation of the topographic effect. So again, we can do the same, so we can put this equation now in the equation of continuity, exactly as we did before.
Can you say the conclusion again?
This one. So, like before, we said, in first approximation, the solution is geostrophy. So if I put the solution of geostrophy here and here, what I obtain is a second derivative term in t and y and in t and x of eta. So the solution will be again the dominant geostrophic flow plus a perturbation. And again I have u and v, which are only function of eta. So u and v, the two velocity components, are function of eta. So since they are singularly function of eta, I can put u and v inside the continuity equation, and so to have a equation only for eta, which is this one. So d eta dt minus r squared dt, again Laplacian of eta, plus alpha 0 gf d eta dx. So now let's look at this. Look at the one for the Rossby wave. You see, it's exactly the same. No, not exactly. Except that this term here, minus beta 0 r squared, is now alpha 0 gf. Okay? So let me write here, minus beta 0 r squared is alpha 0 g f. And of course, what happened to the dispersion relationship? Exactly the same with the first parameter, which is not minus beta 0 r squared, but alpha 0 g f. This is exactly the same. Good. So first, wow, I remember that in the Rossby waves the Cx was only negative, so I have only propagation in the westward direction. Not a problem here. So for the topographic waves, they can propagate positive, they can, Cx can be positive or negative, so westward or eastward. And most importantly, has the same sign as alpha 0. What does it mean? So, so if I have this layout here, this is y. This is z. So if this is y, z, y, z. So x is in this direction, okay? So here, alpha 0 is positive, and here, alpha 0 is negative. Okay? Alpha 0 is nothing more than the way, I mean the gradient of the topography. So if I'm going in this direction, I'm adding fluid height. Okay? If I'm going in the other direction, I'm decreasing the fluid height. So here Cx is positive and here Cx is negative, because alpha 0 is the only term that has in the northern hemisphere, okay? With F is positive. So all this part here, when I do omega divided by Kx, I obtain alpha 0, which can be positive or negative, F positive in the northern hemisphere, and this part is always all positive. So topographic wave propagate. I need to drink something. Topographic wave propagate in the northern hemisphere with the shallower side on their right, like here. So if we are here, so this is shallow, and this is deep, and this is again shallow. So this can be again sea bottom or mountains, okay? So shallow, it means that it's going towards you. So I'm moving, I'm propagating with the shallower side on my side. If I'm here, exactly the same. So we can say that there is a new analogy. Rossby waves always propagate westward with north on their right, westward. So westward means that 6 is negative, so it means this. So north in this direction, so I'm moving in this direction. So the analogy is shallow north and deep south. Okay? So again, also here we can consider the same. We can rewrite the dispersion relationship, this one, by using the plan Kx and Ky. No? So again, we will have the same considerations over the fact that we will have a maximum value of omega, which is alpha 0 g over 2fr. Okay? So again, we will have a maximum frequency. Above this frequency, we don't have topographic waves. So topographic waves exist only when omega is smaller than this one. Good, so since we have find this very interesting analogy between planetary and topographic waves, we can use this analogy also to make some consideration which can be very useful in the laboratory. So, yeah.
Question? Yeah, sure. Rose waves propagate in the westward.
Yeah.
And the analogy is shallow north and deep south. So from the figure, it's not clear where this one is deep south.
So this is Rossby wave. So Rossby wave is propagating with the north on its right.
Mm.
So the analogy is Rossby propagate with north on its side and south on its left side, while the topographic waves propagates with the shallow side on its right side and the deep side on its right side.
Okay, now.
Okay? So if you look here, the wave is going in your direction.
Mm-hmm.
So with the shallow side on right and deep side on left. Okay, it's always here. It's like It's very similar to the geostrophic, because you remember when we did the geostrophy on the irregular bottom, we found something very similar on the northern hemisphere. On the southern hemisphere is the opposite. And the Rossby has the north on its right and the south on its left.
So for topographic waves, just like Crosby, when you reach W max, the flow is just geostrophic.
When you reach, no, the fluid is geostrophic when you have omega equal to 0. This is nothing more than the maximum value of frequency that you
That's just
can.
the maximum allowed
Exactly.
value, but once it
Exactly.
goes to 0, it's back to
Exactly. So there is a limit. Above this limit, you cannot, there is no topographic nor Rossby waves. Okay? So of course the value is different. The one is depending on beta 0, the other one is depending on alpha 0.
That's the modulus of alpha 0.
Sorry?
The modulus of alpha 0.
Yes, the modulus, yes. Because I want to take only positive value of frequency. Of course, one thing that we can do, I can leave it to you for exercise. You can demonstrate that both for Rossby and for topographic, omega is much smaller than f, which is just working a little bit over the dispersion relationship and playing again with the scale analysis. Okay, so you can do it. I think you can do it also because you will find it on the book. So
Take the question again.
so demonstrate for Kelvin and Poincaré, omega is much larger than f. So we have higher frequency than inertia. For topographic and Rossby, omega is much smaller, so we have low, slow flow fluid on large scale. So you have to demonstrate this by using the dispersion relationship. You can do it, for example, in the Cushman, you will find it. They will do the two long wave and short wave limit. Okay? So just working on this and saying, if I am on the longer waves, RK, so if longer wave means that lambda is much larger than R, so 1K is much larger than R, so RK is much smaller than 1. So if this is much smaller than 1, what happens is that this can be neglected with respect to this. And what you obtain is just alpha 0 GFKX. Find the scale, you will find that this is much smaller than f. With the Rossby wave is more direct. With the topographic is a little bit tricky, but you will find everything on the Cushman. So, just to conclude the lecture about the barotropic waves, we can further analyze this analogy between planetary and topographic waves. So, you remember we defined the potential vorticity as the ratio between the vorticity expressed as the sum of ambient vorticity, which is F, and relative vorticity, which is the vertical component of the vector product of velocity, and the height. Okay, so we defined Q F plus zeta over H. Okay, so we can do it and analyze this for our two cases of perturbation. So F will be F0 plus beta 0 y plus dxb minus dyu, which is zeta, divided by alpha 0 plus, H0 plus alpha 0 y plus eta. Okay, so we can look a little bit on the leading terms of this expression. So in the numerator, we have F0, which scales like capital omega, beta 0 y, which scales like beta 0 L, and the relative vorticity, which scales as U over L, right? So again, if I divide everything by omega, what I obtain is 1 beta 0 L over omega and Rossby. Okay? So these two terms are much smaller than 1, because this is nothing more than the beta parameter, and this is Rossby that we know from the beginning that is much smaller than 1. Same thing in the numerator. So we have H0, alpha 0, L, and delta H. We divide all by H0, and we obtain again 1. Then we have alpha 0, L over H0, and then delta H over H0. So these two terms, again, are much smaller than 1 because of the hypothesis that we have considered. So we can consider, rewrite this, and try to, sorry? So we can rewrite the denominator, by dividing by H0 and multiplying by H0. What I obtain is 1 here, and then these two terms. So I will have 1 over H0 multiplied by all this, F0 plus beta 0y plus dxv minus dy u by 1 plus alpha 0 y over H0 plus eta over H0 to the minus 1. Okay? So I have simply rewritten the expression, the full expression of the potential vorticity by putting everything over the numerator. And now, since these terms here are much smaller than 1, I can use the Taylor expansion. So we'll have 1 over H0, again, F0 plus beta 0 y plus zeta, and then I will have 1 minus alpha 0 y over H0 minus eta over H0. Okay, so all this is extremely easy. We can make one step ahead and try to multiply all these terms. In particular, we will, so don't forget that the leading terms are F0 and 1, okay? Because now we don't have H0. So if I compute this, I can multiply, and just to have one single expression. So all of this by 1, so I can have 1 over H0. So F0 plus beta 0 y plus zeta. And then I can start to multiply this by this.
Zeta or eta?
Zeta, zeta. This is zeta, is the xv minus dy u. Is the relative vorticity. So F0 by this one, so minus alpha 0 F0 H0 y, and this by this minus F0 eta H0. All the other terms are higher order. We can write it order 2. Okay? Because order even smaller than this one, because the leading term, don't forget, this is much smaller than this. We can also say that this is much smaller than this. And this is much smaller than this, and this is much smaller than this. So if I multiply this by this, this by this, this by this, and this by this, they are much smaller than these two terms. Okay? So, what we can find here is that Q is function of y And in particular, we can calculate the gradient of the potential vorticity, which is beta 0 over h0 here, and here minus alpha 0 f0 h0 square. Okay? So the presence of
Potential, what is the name?
potential vorticity is a function of y. Y and y. Okay? And so I can calculate the gradient. So the derivative of q with respect to y. So with respect to the zonal, don't forget that zonal, meridional coordinate is much more. For our purpose, it is very important because over the meridional component, you have the variation of Coriolis, because Coriolis change with latitude. Okay. So this term here is positive, and this term here, there is a minus, here is negative. So these terms contain the perturbation effect. Because if we have beta 0 much smaller than 1, and alpha 0 much smaller than 1, so these two terms can be neglected. So for the geostrophy, I can neglect this term here. And for geostrophy, what I have, simply that Q is equal to F plus zeta divided by H. Or simply F divided by H, if F is much larger than zeta. So the origin, we can also think that the origin of the Rossby waves and the topographic waves stands in the existence of a gradient of the vorticity, of the potential vorticity. So the potential vorticity gradient is what we call the trigger, or as Cushman say, the bouncing effect. So the fact that you have something like the famous stone in the pond that create the wavy phenomenon. And in particular, if we look at this this graph here, so if you take a state of rest, so state of rest means that these can be like isolines, isobars, whatever you like. Okay, so the characteristic of these isolines is that when you go up, you are going toward higher values of potential vorticity. Okay, so for the topographic effect, for the planetary effect, you are going toward north, because Q depends on F, and F increase with the going towards north, because it's sinus of the latitude. If you consider the topographic wave, Q increase when you are going toward the shallow area, the shallow part. Okay? So look at here. So if you consider 1 point here and 1 point here, so if I have a perturbation of the state of rest, which is basically the geostrophic flow, so I'm applying over the geostrophic flow a perturbation, which is in this case the beta effect, in this case the topographic effect. So the beta effect is going to give a perturbation, which is a wavy light perturbation, where this point here is moved northward, and this point here is moved southward. So if this point here is moved northward, so since we are having Q equal F plus zeta divided by H, let's keep H constant. If I have moving towards north, I'm in order to conserve the potential vorticity, because you remember that potential vorticity must be conserved in barotropic flow, I must have a decrease of zeta. So a decrease of zeta means zeta minus negative. Zeta negative means anticyclonic motion. And here the contrary, cyclonic motion. So it means that the parcel here are going to rotate in this direction, the parcel here are going to rotate in this direction. This parcel which stays between, it's like within 2 gears, is doing like this. So it means that goes south. So it goes south, and you do the same exercise with all the parcel over the wave, you will have that there will be a rigid perturbation of this wave in this direction. Because this part will go down, this part will go up, and so you will have a practical transformation so this is one situation, this is the other situation, and this is again. So this one goes down, this one goes up, so it's like this is going here, and so I'm having so all the wave is moving in this direction. Okay? Exactly the same consideration for the topographic wave. Here, for the topographic wave, I consider, for example, zeta as constant, and I work only on F and H. So again, if I'm going towards north, I increase F. To maintain constant Q, I have to increase H. So if I increase H, no, yes, sorry. Sorry. So for, yes, this is shallow, sorry. So if I'm going in this direction, I'm going to increase, yes, I'm going to decrease the H, so let's keep F constant, sorry. So for the topographic waves, keep F constant and work only on zeta and H. So I'm moving in the shallow direction, so I decrease H and I decrease also zeta. So I create another time, an anticyclonic motion. Here the same. I increase H, I increase zeta, and so I have a cyclonic motion. Exactly the same effect. So all the wave is moving rigidly in this direction. Why it is important? Because this gives you the opportunity to make experiments on the beta effect in a tank. Because the topographic effect is analogous to the beta effect, and you can see that you can work on planetary waves by simply creating obstacles or topography, because the effect is exactly the same. So this is the strongest part of the analogy between planetary and topographic waves. They are at the same dispersion relationship, provided that you change the beta 0 R squared with alpha 0 GF. But apart of this, the evolution is exactly the same. Standing on the analogy, north, shallow, south, deeper. Okay. So the caption says, comparison on the physical mechanisms that propel planetary topographic waves. Displaced fluid parcels react to their new location by developing either clockwise or counterclockwise vorticity, and intermediate parcels are entrained by neighboring vortices, and the wave progress forward in this direction.
Sorry. So the only, not the only difference, the major difference between the
Planetary.
yes, the planetary wave and topographic wave is what drives them. One is the beta effect and one is just topography.
Exactly. In the dispersion,
It's the same.
you have exactly the same, just don't forget to change this. The problem is that if you want to study the planetary waves in a tank, it won't be able because it is too difficult to create.
Beta effect.
So a beta plane is very difficult to create in a laboratory. But this, you can do it. So you can create a tank with a smaller topographic effect, with the alpha 0 as small as you want. And with this, the same effect of the topography, you can also have it on the Rossby. Okay? So it's a very powerful analogy, especially if you want to work on a rotating tank.
Sorry, just to clear, when you talk about beta effect, it's just moving away from the F plane, yeah?
It's just, sorry?
Moving away from the F plane.
Moving away from the F plane, exactly. So, beta effect is when you have the beta plane.
Okay.
When you have the beta plane, you have to consider a gradient of the df, of the Coriolis parameter. So df dy is equal to beta 0.
Right. And again, just to be clear, when you keep saying a planetary wave, you're saying Rossby waves.
Planetary waves or Rossby waves, exactly. Exactly the same, yes, yes. Both of them, I mean, some of them are have two numbers. Like Poincaré, they are called Poincaré or inertia gravity waves. It depends. It's important to know all the names, but don't be slave of names. Just remember, of course, then, if you are in some conference and people talk about Rossby waves, you know what is this, but say, my wave, no, it's not your wave, it's Rossby wave, okay? Okay, so, with this we have finished the part of the course where we have very much worked and see all the effect related to the rotation. Now, as said at the beginning of the course, we have also to make, not so much, but a few minutes today and next week, we will do something on the stratification. I don't think we will finish everything. Peace. Amen. I have to say. But there will be, I hope to give you at least the basic part, basic information. So the first thing that we have to consider with the stratification is that we are completely changing the framework. So the framework that we are used to see in the for the rotation was the vertical rigidity. You remember that one of the most important things is this one. So there is no shear. The only point where we found the shear was. Sorry. Right. Right. When we have Ekman other than 1. Okay, but it's very small, very small layer. And only other case we have barotropic, and barotropicity is basically built on this theorem, which was the Taylor-Prudman theorem. So now, the fact that we have vertical rigidity, it means that our flows are exactly the same, moving without any change in the vertical. What's happening with the stratification? Completely different. So for rotation, we have that delta x is equal to 0. For stratification, all the derivative must be different from 0 because we are having a variation along the vertical given by the fact that we have a function of z of the density perturbation, while we can consider, at least for the moment, that the variation along the horizontal are equal to 0. Okay, so we are allowed, at least for the beginning, to consider only what happened along the vertical, and to consider this as symmetric in the horizontal. So rotation was very important to characterize horizontal flow, large-scale horizontal flow. Stratification is what you have usually at smaller scale, but h, you remember, that h was already much smaller than L. So the vertical scale, the vertical length scale or height scale is much smaller for GFD with respect to the horizontal one. So the first thing that we want to do is, let's consider this let's consider a parcel which has a certain density rho z and is moved to an area when the density is rho z plus h. So this this vertical distance is h. So this parcel here, since we are dealing with incompressible flows, it will retain its density, okay? We don't change the density, but we'll feel the density of the ambient, because before I had always the same density. The density was not changing. So any problem I had with I didn't have any problem with moving vertically parcels. Now I'm having that this density, this parcel here, which is moved up, will feel something. So can you imagine what will happen? So think about like if you have a balloon, you take a balloon, you put in the water, and you leave. What happened? Why?
Because of the
It's less dense, or? Exactly, buoyancy. Buoyancy is the force that we have to deal with. So, if we write F, our law of motion, force is equal to mass multiplied by acceleration. So we have that the mass of our parcel is rho 0 multiplied by its volume. The acceleration will be the second derivative in time of h, okay? So how h change in time is the velocity, how the velocity change in time is the acceleration, which is equal to the buoyancy force. And the buoyancy force is G rho z plus h minus rho z multiplied by v. Okay? So if the difference between the density, the weight of the fluid with respect to the weight, the weight of the parcel with respect of the object that we are dealing with respect to the weight of the ambient fluid. So this will be, is constant. This is fluid and this is the parcel. So this is our balloon, okay? So if this is smaller than this one, this will be positive. Boom. Okay? The contrary will go down. Okay, so we can work without considering the volume. We have the Boussinesq approximation. Just give me a few minutes to finish. So we can consider rho z as rho 0 and rho z plus h as the perturbation of rho z plus the rho the z to h. So this is a perturbation of the density field plus the first order of the Taylor expansion. So if we substitute here, we will have rho 0, second derivative of h, equal to g. So the difference of this is just this term here, d rho dz multiplied by h. Okay? So d rho dz actually is the gradient of the density field. So if we have something which goes like this, so this is rho and this is z, it means that we have heavier fluid on the bottom and lighter fluid on the top. The contrary will be lighter fluid on the bottom and heavier fluid on the top. So in this situation here, what do you think? Is it stable or unstable?
The first one is stable, and the second one is unstable.
First is stable, the second one is unstable. Right, because if this is heavier, there will be some, sooner or later, it will start to create, and so this will go down, and this will go up, because equilibrium must be conserved. So, in order to have this unstable situation, I must have to give something, to give energy, in order to keep this situation. This is the natural situation. Okay, so we can rewrite this, and we have second derivative minus g rho 0 d rho dz h equal to 0. So we have the two cases. So the first case when d rho over dz is positive. No, sorry, contrary, is negative. So when d rho over dz is negative, it means that we are decreasing rho with respect to z. So, as you said, we are in the stable according to our intuition. So the rho dz is negative means that minus g rho 0 d rho dz, which I will call capital N squared, is positive. Right? So this is negative, this is positive. So this N squared, any of you knows the name? N squared. So the dimension of this N squared is rho and rho is 0. Then we have G over length. So it's rho and rho can be neglected.
1 over second square.
Or second square.
Sorry?
1 over second square.
1
Meter seconds.
1 over second square.
second square. Second to the minus 2. Right. So it's a frequency. It's a frequency squared. So N is a frequency. Do you remember the name? Yes. Do you remember the name? No, you know. But the meteorologician, come on. Brunt-Weisela frequency.
Yes, pumpkin squares is everything. These are the frequencies.
Never forget, this will be your best, after Coriolis parameter, this will be your another best friend. Okay? Okay, so when we have this, and we put here the solution,
Sir, the name.
sorry?
The name.
The name, Brunt-Weisela. Brunt-Weisela. So it's the name of two scientists. Brunt is from UK and Weisela from Finland. So last thing, and then I stop. So if I put this in the equation, I will have h. I use the double points to represent the second time derivative, plus n square h equal to 0. What is the solution of this? H equal h0, a complex exponential entity. So physically, what happened? We have our parcel, which is heavier. So it's moved up. It's heavier than the surrounding because it comes from a heavier area. So it's here. Okay, so this is my parcel. I move it here. So my parcel is feeling heavier than the surrounding. So go down. But go down, acquire vertical velocity. Thanks to its inertia, overcome the equilibrium and go down when it will be lighter than the surrounding. And so it will go up. Down and up. Oscillation. So the stability gives us oscillation. Of course, if we do the same, putting delta rho positive, we have the instability, and the solution will be
Exponential.
a real exponential. Because in this other case, I will have that my parcel will always be lighter than the environment. So if it is lighter, it will go up. And we'll do like this. And of course, all the parcel will do like this. And so I will have this convection phenomenon. Okay? Okay. What do we see?
No, Monday.
Ah, yes, you're right. I was accustomed to say tomorrow.